Good morning, ladies and gentlemen. Welcome to the third session of our Expert On webinar series on the low carbon application of wheat straw building materials. I am your host in English and Chinese to English interpreter, Jia Li. For better efficiency, we use simultaneous translation, which means there will be a channel in English and a channel in Chinese. For our Chinese audience, the webinar will be broadcasted live via Sina platform and automatically chosen Chinese. For audience from EU and UK, you are using Zoom, and please choose the English channel by using the translation button on the bottom right corner. Carbon neutrality or net zero is now a relatively familiar topic. This webinar aims at providing a platform for researchers in China and UK, EU to share their learning and experiences. The webinar series is hosted by China Ecological Building Material Association, Arcus and Callisto Consulting, and Future Built. The Ecological Building Material Association is a branch of the China Building Material Federation. Their work relies on the technical strength of the Environmental Material Science Research Team of the China Building Material Academy and the State Key Laboratory of Green Building Materials. They focus on promoting green, low-carbon, ecological, and healthy building material products and technologies and its industry development. Biomass building materials is one of the green and low carbon building material that the branch promotes. It leads and regulates the development of straw and other agricultural waste recycling building materials through national scientific research projects, standard formulation, and organization of industry forums. Today's expert speakers and their topics are Professor Jihao Chen on the low carbon application of wheat straw building material and development, Professor Luming Wang on low carbon environmental impact of wheat straw building material and the development of wheat straw ecological building material, Dr. Sayed Ghaffar on high performance compressed straw board. After the experts' presentations, we will summarize questions from both platforms and ask our experts. The speakers' stands do not represent organizers. Audience on Zoom, please use the chat box to post your comments and questions, and at the same time, you can scan the QR code on top to join our WeChat group or on the bottom for our LinkedIn group to continue the discussion. Last but not least, this webinar series is sponsored by Beijing Huangsha Building Material Technology Ltd. Beijing Huangsha is a high-tech, light asset enterprise with international vision that provides services in technology R&D, intellectual property rights, and integrated systematic solutions in the field of carbon neutrality, circular economy, and solid waste management. Now let's watch today's first presentation from Professor Jihao Chen on the low carbon application of wheat straw building material and development.
秸秆建材减碳技术应用及发展展望。我要讲的主要内容呢，就是背景和几种秸秆建材的发展情况，以及秸秆建材发展当中存在的一些问题。另外对秸秆及建材呢进行一个展望。 那么我国呢，跟世界主要国家比，我们的碳排放量占比是比较高的。2019年的数据是26.7%， 2010年到2019年的排放量是26%。我们国家呢，也在2020年9月，国家主席在第75届联合国大会上承诺，中国二氧化碳排放力争在2030年达到峰值，2060年呢实现碳中和。那么我们作为建筑行业呢，比较关注就是农业固碳的这个方式。我们中国呢是一个农业大国，每年秸秆可收集量，约9亿吨，秸秆每年焚烧量要达到8000多万吨，碳排放也能达到3450万吨，是一个很大的数。那么秸秆呢，主要是以玉米秸、稻秸、麦秸这3种为主，还有其他一些秸秆。这个秸秆呢，就是五化利用，就是主要是肥料、饲料，还有这个燃料化用的比较多，其他呢用的比较少。大约有19%的呢焚烧和废弃。那么我们建材行业呢，如果要想减碳，就是说，每年年生的这些秸秆产生这些秸秆，把秸秆这个产生的碳汇能够给它固定下来，那么作为建材是一个比较好的途径，它能够大量利用秸秆。那么秸秆呢，如果要是作为建材呢，它有几个特点。第一个是它是可再生无污染，另外一个它低廉易得，保温性比较好。另外呢，它还有一个轻质、强度高和柔韧性提高。另外它就是能够制成大块，可以提高施工效率。那么我们中国呢，每年有10到15亿平方米的新建建筑，对建筑材料呢有大量的需求。下面我讲几种秸秆及建材的发展情况。首先就是秸秆草砖房。秸秆草砖房呢，作为建筑应用出现的时候，是在19世纪，在美国，当时是为了解决木材短缺的问题。前前后后建造了有1万多座秸秆建筑，现存的建筑，超过100年。那么秸秆草砖房呢，在我们国家20世纪90年代初期呢，由于这个秸秆的超低能耗，舒适性，重新在美国得到发展。同时呢，在加拿大、澳大利亚、奥地利等国呢，也开始得到一些发展。但是秸秆建筑有一个特点，它就是适用于农村建筑。另外，它由于这个运输方面的问题，所以它只能建造2层以下的建筑。这是国外的一些发展情况。那么我们国家呢，在2000年前后，通过安泽国际救援会引入了这个草砖房的技术，在东北呢，大约建设了有700多座秸秆草砖建筑，包括小学啊、那个住宅啊这种。秸秆草砖房呢，并没有在这个过程当中得到大量应用。那么它的问题呢，主要还是这个生产运输的问题的限制。那么现在呢，我们有企业已经对它进行了改进，比方说天津香景建筑已经在这个制造方面进行了改进，那么它得到了工厂化生产、现场吊装拼接的生产模式。主体建筑2、3天就能完成，1周之内就能达到很高的这个完成度。 这是一些秸秆建筑的应用案例，在国内的。另外一种呢，就是秸秆复合墙板。那么我们国家呢，在80年代曾经从英国引进了2条稻草板生产线，建在了辽宁省营口市1条。这些厂区呢，主要是用这个纸面稻草板建造的，现存的呢也有36年之久，稻草板依然完好。这个稻草板呢，当时建造的时候呢，由于是这个为了解决这个住房短缺的问题，所以单层秸秆板是两面抹灰，达不到现在建筑节能的要求，所以逐渐就停止了。那么这种技术呢，在国内也得到这个消化吸收，国内的改进方式呢，就是通过高温高压挤压成型的这个秸秆芯板呢，粘贴无机面层，形成复合板。那么这种方式呢，就地取材可再生，秸秆利用率比较高，克服了这个秸秆草砖抹灰结构运输和它这个高度限制的这些缺陷，能和轻钢结构有良好的结合。那么秸秆经过复合无机面层呢，可以秸秆的利用率非常高，能达到80%以上。秸秆的大量应用问题就得到了一定的解决。当然了，这种板材呢，如果应用大家关心的几个问题，就像隔热呀、燃烧啊，还有这个防潮耐腐这些方面的性能，我们也做了一些测试。通过测试就发现，如果要是用双层墙体的话，它的传热系数能达到0.34，达到了现在建筑节能75%的要求。那么我们对它的隔声性能呢也进行了测试，测试的结果就显示，如果要是双层墙体，那么它的隔声性能能够达到比较高的这个级别，基本达到外墙应用的这个要求。那么它的燃烧性能呢？我们经过这个对墙体的测试，它的燃烧性能达到了 B1级，并且在燃烧增长率指数、总热释放量方面、烟气生成指数等方面都比较有好的这个更优的性能。这是它的耐火性能，2个小时的耐火极限测试显示背面完整，并且最高温升只有24.4度，远高于标准140度的要求。那么秸秆复合墙体的防霉性能呢，也是很受关注，因为毕竟我们这个建筑是要存在好几十年的，我们对它的这个防潮性能和那个防霉菌性能进行了测试，就是在比较高的湿度环境下，秸秆板新材呢重量增加不超过4%，另外它的耐霉菌也能达到2级，如果要是添加这个防霉材料之后，能达到0级。我们对这个秸秆复合墙体的耐候性能也进行了测试，测试就是在热雨循环80次、冷循环5次、高湿条件7天的情况下呢，它的外表保持完好，没有这个粉化、空鼓、剥落这些缺陷。这也是它的一些应用案例，包括这个新农村建设呀、旅游地产开发呀，还有木结构房屋啊这种。当然了，它也可以用于内墙，而且这个用于内墙做构件的话呢，能够提供一个快速施工、工厂化生产的这么一个条件。另外一种利用秸秆的板材呢，就是植物纤维水泥墙板，这种是主要利用农林废弃物对这个农林废弃物粉碎 改进粉碎进行无机改性之后，作为填料添加到这个板材当中，形成植物纤维水泥墙板。这个它有一个比较好的特点，就是那个添加量是比较大，所以最后形成的这个板材比较轻质。另外呢，它也能够大比例的使这个秸秆得到应用。所以呢，其实是一种比较好的固碳方式。同时呢，它又能达到传统秸秆传统建材的这些性能，不用担心它的这个燃烧性能啊，其他性能。就是植物纤维水泥板的隔热性能呢，我们也进行了一些这个测试。就是单排孔呢，它能达到1.01瓦每平方米每 K，然后双排孔，200毫米厚，如果要是加上这个 EPS 保温板的话呢，才能达到0.45瓦每平方米每 K， 也能达到这个建筑节能60%的要求。当然了，它的燃烧性能，因为还是主要是无机材料，所以它能达到 A1级，耐火极限呢也能达到2小时。然后它在主要是河北、山东、天津一带得到了比较广泛的应用。作为这个墙板呢，受到的限制比较少，而且也证明了这个几年的这个工程，也证明了它的这个性能是没有问题的。另外呢，秸秆基建材，我们刚才提到了大量应用，其实是我们还是想高值化应用。如果是高值化应用的呢，国内还有一种技术就是常温冷压成型秸秆人造板。那么这种秸秆人造板呢，是通过无机胶粘剂，高压常温之下成型，在压力锁定机具当中成型，形成秸秆板材。它最大的优点就是生产过程比较环保节能。那么通过符合其他面层，包括这个卷脂面层啊，还有这个阻燃层啊，形成了系列化的这个产品。这种产品呢，在常温状态下就能够胶合，并且它胶合过程当中释放的热呢，就对板皮进行干燥，所以整个过程呢比较节能。这是不同的秸秆人造板的产品。那么这种产品呢，由于它的良好的阻燃性能，也已经应用于江苏大剧院啊、深圳万科、深圳华为高配中心这些项目，应用超过这个2万平米。现在呢，他们有一部分产品开始出口，在18年呢获得全国绿色低碳领域最具投资价值领先技术蓝天奖。那也是一个比较有影响力的奖。那么秸秆建材发展当中的瓶颈问题呢，我们认为是2个问题对这个秸秆基建材产生了比较大的影响。一个就是秸秆有一个收储运的，制约了它的规模化发展。那么一个是它的季节性影响生产的这个连续性。另外，由于它的这个运输半径、储存场地要求都比较高，储存场地要求非常大，有安全方面，比方火灾啊之类的问题，所以呢，收储运是制约这些技术发展的一个关键问题。那么这种情况要解决呢，那就是要采取合适的规模，根据它的运输半径，采取合适的规模来进行生产。另外一个问题呢，就是秸秆基建材的标准规范还不是很完善，是制约它进入建筑市场的一个瓶颈。那么如果要是一个秸秆强材要想进入这个建筑领域，首先它需要有这个产品标准施工规范、图集等等，所以也给这个秸秆产业的发展呢造成了一定的阻碍。 为了解决这个问题呢，我们在17年和14年立了2项行业标准，一个叫秸秆复合墙板，一个是植物纤维水泥墙板。这2个行业标准呢，都已经在2021年报批和公示，基本解决了它产品标准的问题。另外呢，我们还做了一个植物生态复合板建筑模块应用技术规程，是解决它施工当中的问题。那么当然还要结合具体的进行这个图集的设计，来达到这个解决市场准入的问题。那么市场铺开之后呢，我们这个制造是没有问题，那么这个秸秆建材呢，还是有比较大的发展空间。秸秆基建材呢，我们认为，它的发展还是有很大的空间。第一个是，就是因为这个秸秆，在建筑领域得到大量应用，那么是比较好的一个解决方式，在其他领域能得到大量应用就比较难。那么，它的发展会是什么样子呢？我们也做一个预测，就是我们认为是高附加值的秸秆基建材，比如说人造板，将会率先得到发展。另外一个呢，就是在钛减排的大背景之下，它尤其显示了它的固碳、减排的这个生态优势将会得到发展。另外就是就地取材，在农村推广秸秆基建筑比较有优势。这就是我讲的主要内容。好，谢谢大家。
All right, thank you very much, Professor Chen. Now I would like to take this opportunity to introduce Arcus and Callisto Consulting to you. Arcus and Callisto is an international consultancy in London, England. The company has its team in London, UK, Beijing and Shenzhen, China. ANC is committed to promoting technology transfer and learning exchanges in the construction and building material industry between China and UK. Our core services include market development, agency and introduction services, translation, online, offline training services, and communication activities, etc. Please scan for our official WeChat and LinkedIn account, as well as visit our website. Audience on Zoom, please use the chat box to post questions and comments for the Q&A session. And you can also scan the QR code on the top to join our WeChat group or the bottom for our LinkedIn group. Now let's watch presentation from Professor Lu Ming Wang on low carbon environmental impact of wheat straw building materials and the development of wheat straw ecological building material.
"尊敬的各位专家，大家下午好！很荣幸有机会参与本次中英秸秆建材减碳应用交流会。首先，请允许我做个自我介绍。我叫王路明，来自中国江苏盐城工学院，目前担任该校的副校长，是江苏省生态秸秆建材研究工程中心的主任，江苏省绿色基础材料服务平台负责人，从事秸秆建材的技术研发以及购废资源化利用有20多年历史。我今天要给大家汇报的题目是秸秆建材的减碳生产效应 与秸秆生产进程开发。以上以下6个方面进行汇报。首先向大家汇报的第一个方面，项目的研究背景。世界农作物秸秆资源丰富且可再生，每年产生约50亿吨秸秆，其中中国约9亿吨。世界范围的巨量秸秆废弃物对生态环境造成严重的破坏，亟待处置。目前，秸秆利用率低下，中国每年有80%以上的秸秆用于还田，长期还田利用导致土壤结构严重破坏。也有少量的秸秆用于发电、制肥、制气和饲料等。由于种种技术限制，其利用率有限，微不足道。当今世界木材资源贫乏，大规模的房屋建筑和基础设施建设面临着严重的建材资源短缺的问题。秸秆还有丰富的木质纤维素，具有较好的韧性和抗烂强度，是混土重要的增强基带材料。秸秆密度小，强动比高，隔离保温、隔音、数据量大，可再生，无污染，是理想的生态建造节能材料。保护森林资源和开发利用秸秆资源是世界范围的共同课题。用农作物秸秆替代木材原料和原传统的强基材料，是实现我国林业和建筑业可持续发展、缓解木材和建筑原料供应不足矛盾的有效基础。由秸秆建成的秸秆建筑可实现完全意义上的生态被动防护，其节能效率高达80%以上。属于第二森林之称的秸秆资源必将成为新的绿色钢筋和绿色混凝土，一个绿色建筑的新时代即将到来。汇报的第3个方面，秸秆建材具有显著的减碳生产效应。农作物秸秆是根系水通过光合作用吸收大气二氧化碳而形成的，同时释放出氧气。只要秸秆不降解、不风化，秸秆中的二氧化碳就回不到大气中去。将秸秆制备成建筑材料，永久封存，就可将碳永远固定在秸秆建筑之中，打破农作物自然界的碳循环链条。据粗略估算，一吨秸秆通过光合作用可吸纳大气中的二氧化碳是1.5吨。中国秸秆每年可吸纳13.5亿吨二氧化碳，全球秸秆的产量每年可吸纳75亿吨二氧化碳。秸秆现代化是人类能够有效吸纳大气二氧化碳，降低温室效应，实现碳达峰、碳中和的最有效措施和现实路径之一。汇报的第4方面，在经 秸秆生态建材技术开发方面，我们建有国内唯一一个专业从事秸秆建材技术研发、研究与开发的省级平台——江苏省秸秆生态建材工程研究中心，拥有150亩土地的江苏秸秆生态建材科技成员，新材料及技术研究、功能实际、技术与产品开发、性能检测、成果推广及应用于一体的高水平秸秆生态建材技术研发平台与成果转化基地。目前已建成年产10万立方米秸秆墙板生产线1条。经过数十年的攻关和研究，我们取得了一系列的重要的理论与技术成果，一批关键技术处于国际领先水平，获多项国家部委的以及省级的重要科学技术奖励，与中国建材研究总院联合制定了建设行业标准秸秆复合墙板。秸秆作为建筑材料使用，面临着多个关键科学与技术难题。秸秆长期处在自然环境下，会受到各种因素的影响和侵蚀，易发生霉变、腐朽、降解和老化。秸秆与现代主要的胶林材料的结合，存在着诸多的不适应性。聚合类胶材料其耐力和防护性能差，易老化，而且造价高。硅水岩、水泥等强碱性水泥会促进秸秆的降解与腐朽。石膏、石灰等基型胶印材料耐水性能差。所以，提高秸秆的抗霉变、抗腐朽、抗降解、阻连、耐水等主要耐久性的问题，是我们将秸秆作为建筑材料的最主要的努力方向。我们取得的主要的技术突破和技术创新有：一是合成多功能的新型无机复合胶印体系，克服秸秆霉变、腐朽、降解和老化等环境耐用差的重大科学与技术难题，使秸秆真正变成建筑资源成为可能。二是采用了耦合与果肤技术，解决了无机胶印材料与生物质秸秆界面结合与融合的技术难题。三是采取新型的粉碎、搅拌与成型技术，有效解决秸秆均质化搅拌以及快速成型技术难的问题。自制的秸秆板材同时具备了轻质、高强、环保、保温、隔离、隔音、防腐、防虫、防蛀、防火、防潮、耐水、抗冻、抗力、抗震以及价格低廉等一系列的优良中性，各项技术指标全面达到或超过行业标准的技术要求，而且品质稳定可靠。秸秆生的这种板材可广泛的应用于工业与民用中的内外墙体、铺面、吊顶、地板、 装饰装修板、门芯板、保温板、防护板等。我们主要的产品形式有秸秆均质内外墙板、秸秆砂架后墙板、秸秆装饰一体板、秸秆家装家具板，以及秸秆的地板以及秸秆的欧米板等。要汇报的最后一个问题，秸秆是在建材的发展具有重大的经济与社会意义。传统建材生产与使用存在着环境污染严重、能源消耗巨大、资源过度开发等严重的问题，并且建筑物的质重大，性能与环境有很差。而新型秸秆生态建材的生产和使用具有秸秆利用率高、节约资源、保护环境等诸多优越性能。秸秆建筑节能环保、抗震、生态宜居。秸秆生态建材技术的突破及广泛应用，必将为中国和世界二氧化碳减排重大发展战略做出巨大贡献。最后，我们借助中国国家主席习近平同志在第75届联大的庄重承诺，与大家共勉。
中国为达成应对气候变化巴黎协定做出重要贡献，也是落实巴黎协定的积极践行者。在此，我愿进一步宣布，到2030年，中国单位国内生产总值二氧化碳排放将比2005年下降65%以上。
谢谢各位专家，敬请各位专家给予指导。谢谢。
Okay, thank you very much for Professor Wang. Now I would like to take this opportunity to introduce our partner FutureBuilt. FutureBuilt is the world's largest sustainable building material exhibition and the largest exhibition in the British building material industry. FutureBuilt has been held since 2005, and its main purpose is to showcase the industry's most advanced environmental protection technology, gather top decision makers, and promote the industry's low carbon development. The next FutureBuilt will happen from the 1st of March 2022 to the 3rd of March. There's still spaces right now and they're going fast. If you're interested in exhibiting, please contact Marina Stewart via the email or just go on FutureBuilt's website at futurebuilt.co.uk. Once again, allow me to remind audience on Zoom, please use the chat box to post questions and comments for the Q&A session. You can also scan the QR code on the top to join our WeChat group or on the bottom for our LinkedIn group to continue the discussion. Now, let's welcome the last presentation from Dr. Sayed Ghaffar on high-performance compressed straw board.
Hello again. Thank you very much for tuning in. I will be now talking about high performance compressed straw board and in general, bio-based construction materials, and some of my previous experience and previous research projects that are around these topics. So bio-based materials, obviously we have a lot of options in the nature that we can build with, but the main challenge, the main problem with bio-based materials is their technical performance. And with the help of science, with the help of material science, there are a couple of interventions that can help us to bridge the performance gap between bio-based materials and conventional materials that are made from petrochemical resources and resources that generally tend to have a lot of negative environmental impact. So my research goal in this area is to develop new generation of high performance and sustainable construction materials. The focus of today's talk will be on super strength straw building materials. A lot of, for example, wheat straw after the harvest of the grain gets left on the field, and after a while it's burnt, which obviously results in a lot of CO2 emissions. And what we have done in this project is we have proposed to use the stem of wheat straw for construction materials, and I will go into the details of how we managed to utilize such materials and how we were able to actually come up with a pre-treatment that can enhance the performance of such material in the context of bio-based composites. So these are just some of my main motivations. Of course, this is known to everyone. These are sort of the headlines that actually showcase the significance of my research efforts. We have high global demands for energy, unstable and uncertain petroleum sources, concerns over the climate change, of course, global warming. With the latest reports we saw last week that there are many pressing issues, and it is now past the emergency, and everybody needs to play their part in changing the attitude and hopefully trying to come up with a mitigation plan to the concerns and to the changes to the climate that we are seeing now, we are experiencing now. Obviously, the main underpinning reason for all of this, all of these challenges, is overpopulation and the lack of control that we've had throughout the past centuries. That then leads to air pollution. Then with the globalization, with the overpopulation, of course, we are using a lot of our natural resources. So we have a crisis there. And at the same time, we are producing an excessive amount of waste, whether that is waste coming from municipal solid waste or our industry, which is construction and demolition waste. So these are just some of the main headlines that are showing the motivation for such research and why we need to move towards spending investment and time and research in utilizing our natural resources and how we can go back and help construct with them. So bio-based materials, building materials, they obviously expand the use of low environmental impact materials, which is certainly a very good and positive move in the right direction. And these alternative materials, of course, they have to be non-polluting, they have eventually be recyclable, and most importantly, locally available. So there is no point in importing, for example, wheat straw from another part of the world just to make a compressed straw board out of it. It just doesn't make sense. It has to be locally available. Otherwise, the whole motivation or the whole idea behind these type of developments is just not worthwhile at the end of it. So these are the main characteristics of bio-based building materials. And I want to give an example of what we did back in 2013 on a project called Grow to Build. So this is actually a long time ago now, 6 years ago now. This project was funded by ERDF, which is European Regional Development Fund. And we were basically focusing on the transition of Northwest European economy from an oil-based economy towards a bio-based economy. So how can we encourage, for example, more farmers to grow hemp and flax and wheat straw, and show them that there is a light and there is a way of making a building product out of these crops. We try to tackle the whole supply chain in this project, from the farmers all the way to the processing partners, the stakeholders, composite making partners, the companies who are using these fibers and putting them in the form of a building block, for instance, and how we can make sure that they are talking to each other, they are communicating their needs, their requirements, so that we can have a perfect solution to transition the European economy from an oil-based to a bio-based economy. And I have to say that it was a successful project. We are looking to expand on the outcomes, and we have expanded on what we learned during that project. We had 11 European partners from Northwest European countries, the likes of Netherlands, Belgium, France, and obviously we had a couple of partners in the United Kingdom where we are from and I am from. So in Brunel at my university, we were actually in charge of dissemination of such knowledge, and we were also in charge of technical development of these bio-based building products. And in the next slide, I have a couple of pictures that hopefully can showcase what we achieved with this project, Grow to Build. So we developed European Center of Excellence, where we display all different kinds of examples and prototypes of bio-based building products, biocomposites. So for example, here you're looking at the hempcrete. So we combine hemp with limestone. So this is just some of hemp, some limestone with some water, and then you just pour it in a mold. And after 24 hours, you have your building block. Obviously, they have great thermal insulation properties, but their mechanical performance is not is not comparable, let's say, to obviously a Portland cement counterpart or a building block. But of course, we can reinforce them. We can use them for non-load bearing applications. And here, for instance, you are looking at another product that we developed called WPC, wood plastic composite. The wood waste is from furniture. And we also used polymers that have been recycled, the likes of PP, polypropylene, polyethylene, and some recycled PVC, actually, polyvinyl chloride. And we used this darker color here is, it has some waste tire rubber, so shredded tire rubber, in a process called extrusion at high temperatures, 200 degrees Celsius, 190 to 200 degrees Celsius. And we used extrusion, and the profiles that you can see here can be used for decking, external decking. We also produce a lot of documentations, a lot of technical data are displayed here. We display them for all the small and medium enterprises, all the architects who are willing to learn more about these options and these alternative solutions. They do come into us, to our European Center of Excellence, and we exchange our knowledge, and we tend to do a lot of consultations on their request and on their product developments. We also tend to have a lot of conferences, a lot of workshops where we meet technical directors of different companies who are interested in investing in bio-based building products. And we also have a lot of raw materials on display. These are some hemp chips, flax fibers, wheat straw, and we have all the technical specification and all the characteristics of these fibers, the likes of things like chemical composition, things like mechanical strength, and all the important critical parameters that somebody who is trying to develop a product needs to know and needs to have before they design a formulation, and after testing that they can achieve the required performance and properties. So for example, you are looking at hemp chips. Different types of hemp chips are available at Grow to Build in our European Center of Excellence. And as I said, we have all their technical specifications. Again, this is another close-up of a hemp chip. This is a picture of hempcrete, so the hemp chip that has been combined and mixed with limestone. and hydrated after 24 hours into a solid building block. Some straws, wheat straws in this case, which is obviously the main topic of today. We looked at the material science of wheat straw and how we can identify the good parts within these stems, that they are useful for withstanding high structural loads in a context of bio-based composite. And you can see some other examples of the products that we have developed. So let's go to discuss the wheat straw composite, which is really the main topic of today's session. And if you're interested, I will obviously make all these presentations as slides available to you, so you can read what we have done, what my group has done already in this around this topic. Before we get into it, I just want to show you some examples of different companies that have used wheat straw for their panel construction. But one thing that I want you to realize is that they do not use any pre-treatment, they do not use any material science. They just get the wheat straw without minimum processing, without any separation, without any cleaning, without any purification. They just use it in a cassette, as you can see in the picture, and they put it in use. Obviously, their durability then is an issue. Their mechanical performances then is another issue. But this is how they utilize wheat straw without any pre-treatments, without any optimization. And I will tell you why this is wrong, and I will tell you why this will not be a good solution in the long term and at a large scale. These are only one or two examples of the projects that they have done, and it might not be suitable or feasible, let's say, for industrial upscaling. So you can see some more pictures here of this company. The link is here, and the company is called EcoPanel. And this is their information. They are based in Czech Republic. So my project, a little bit more about my project, high performance compressor straw boards. We got the sponsorship from EPSRC, Engineering and Physical Research Council. I have two industrial partners on this project, and it will end January 2022. It started in 2019. So today I will talk to you about the outcomes of what we have found out from this investment, from this project. The main focus is on biorefinery of wheat straw. So the process of biorefinery is a sustainable processing of straw biomass into a spectrum of marketable products and energy, the likes of heat, power, fuels, chemicals, and also some materials and some products that we can extract from this straw biomass. So there needs to be a biorefinery process. There needs to be a pre-treatment stage. There needs to be a processing and optimization before we can manage to achieve an array of different products and different energies useful for our sustainable development. So the target is on low volume, high value products, in addition to high volume, low value products like bioethanol, which is fairly an established area of research and development. It has already been developed, and they have very high TRLs. Technology readiness level is quite high. And I know a lot of companies who are actually using bioethanol, which is coming from straw biomass or coming from wood. So our target was on materials and how we can get from a straw biomass through a biorefinery process, a material that can be served for the construction industry. The project concept summary is that we are focusing on an improved lightweight compressed straw board, and they have to be strong enough to accommodate the structural loads both in tension and under compression. The project will try to exploit a novel concept of industrially efficient and selective removal of defects. I will explain what these defects are in the context of straw. And we want to use processes that are easily scalable and can be industrially feasible. And once we have done the optimization, once we have such a removing mechanism of defects, we can improve the surface quality of the straw, because when it comes to biocomposite, I explained why the surface is such an important element for achieving high mechanical strength. So these are what we are trying to target, what we have tried to achieve, and I am pleased to say that we are able to now produce these compressed straw boards that have very high mechanical strength and physical performance. So their water absorption, for instance, is very good, and it passes all the different types of standards. This is the project concept diagram. We are looking at modular system. So we want to focus on small scale modular blocks for prefabricated construction. The company, the project partner who is contributing to this project is giving us their trust. So you can see in the presentation here that the company name is SpaceLink, and they have developed these type of trusses that our compressed straw board, our panels will actually fit in the middle of these trusses, and they will help us to have higher mechanical strength, especially in tension. One of the main work packages is on raw material optimization and how we can detect these defects within the straw stem. Then we integrate the compressed straw board with a SpaceLink solution. The pre-treatment cycle is extremely important, and we have to adopt a strategy which is environmentally friendly. And after that is a comprehensive testing and validation of our solution. This diagram here shows the details of the board packages. It starts from raw material characterization. Then the outcome of this board package was fed into work package 2, which is selective separation and processing for the optimization of the materials. Then work package 3 looks at a manufacturing process development for prototyping. And obviously we did a work package that analyzes all of these properties and is a very comprehensive characterization and testing in order to evaluate the impact and see if we can produce the system and the solution on an industrially feasible scale. So we wanted to use eco-sustainable strategies. We knew that the wheat straw as it comes is not strong enough. It needs some type of pretreatment, and our pretreatment is a combination of physical methods, very mild physical methods, and we do not use any chemical pretreatments, and we do not use any coupling agents. We just use a couple of pretreatments, combination of physical pretreatments such as hot water washing, steam pretreatment, and for the reasons of comparison, we also use microwave and hot water. And UN here stands for untreated straw. So we wanted to get the full picture of what happens to this straw once it is undergoing these different type of physical pretreatments, for us to find out if we can actually enhance the performance of these straws compared to an untreated sample, untreated wheat straw as received from the farm. So we had to look at the wheat straw in detail. So this is the wheat straw stem. Obviously the grain goes for the food purposes. Then you are left with a stem, and the stem has two different main components. One of them is called internode, and the other one is called nodes. So here you can look at the nodes. This is as received from the farm. Then we cleaned all the straw biomass. We got rid of all the leaves, and we were left with a stem. The stem is this part here. Then the next stage, we separated the internode from the nodes. So the nodes are the joints. They act as a joint in the column. And in the context of biocomposite, we later found out that they are defect. They are potential routes for cracks in composite once they are under loading. And I will prove it to you within the next few slides, why these components, so these parts of the wheat straw, are not actually beneficial, and we need to get rid of them. That's why I call it defect. But they have their own use. So this is a diagram that I developed that shows the different valorization pathways for wheat straw. So the main two components of the stem are internode and node. From internode, we can focus on pulp production for the paper industry. Biocomposite, of course, is one of the main areas. They are good for anaerobic digestion and biogas production. We can make pellets, fuel pellets out of them. They are perfect for enzymatic hydrolysis. So we can produce bioethanol and even bioplastics from them. But nodes, on the other hand, they have their own applications. They can be used for lignin extraction, and they can be used for wax extraction. So we can use them for cholesterol reducing agents, flavorings, food supplements, and even cosmetics. And on the other hand, because the node has higher content of lignin, we can use these nodes for lignin extraction and aromatic components and compounds, chemical compounds, that they have their own application. But one thing that I want to emphasize here is that we should not use the whole wheat straw as it comes from the farm. There needs to be a separation. There needs to be a careful characterization between node and internode and what they could be used for. This is a smart way of biorefinery. So in our study, we looked at the morphology and how the different parts of the straw are different. So this is node in transverse direction. If you investigate it from the root to the grain, you can see different cross sections. So if you cut the node in half in a transverse direction, the morphology of the cross section actually changes. So you can see it is initially hollow, then it becomes dense, it becomes very completely filled up. And then you have a very dense core material here at the center of the node. And then later on is the initiation of the upper internode, which is again hollow. And it doesn't have any dense areas. I can show you in the next picture here. So you are looking at the cross-section of internode, and you can see it only has one layer of epidermis, parenchyma, and vascular bundles, and is generally hollow. It has a hollow structure. Again, here it compares the cross sections of nodes in transverse direction. So this is the whole of the node area. It was cut in the middle in a transverse direction. You have the inner surface and the outer surface, and these are the optical microscopy images showing the cross section of the node area. And these are some scanning electron microscopy images of the different parts of the node, which is characterized by brownish colored elliptical shaped rings. And these are what provide a good compressive strength to the whole stem. I also looked at the chemical functional groups on the surface in order to understand the chemistry of wheat straw. We looked at FDIR, so what type of chemical agents or chemical characteristics we have on the node and internode. We found out that wax is an important element on the outer surface, and wax is a hydrophobic element. So if you want to use wheat straw in a context of biocomposite, you need to have a surface that can allow the resin to penetrate inside. But we have an extensive amount of wax on the surface, which diminishes the penetration of resin into the stem. So therefore, we will have a very low mechanical strength. We will have a very low wettability, which is an important element when it comes to biocomposite production. We also had a lot of silicon oxide and silicon carbide in different wavelengths on the outer surface of node and internode, and they are also characteristics of lignin and other chemical components of wheat straw. We compared the morphology of node and internode, and epidermis, which is on the outer surface, contains the most amount of wax. And as I showed you, the wax has its own application, but in the context of biocomposite is actually a defect. We do not wish to have any wax on the outer surface because it inhibits a strong interfacial bonding with the resin system. So you can see that the epidermis is a lot thicker in the node, and that's why one of the reasons why we have to separate the node from internode, because the node in a context of biocomposite acts as a defect. Excuse me. And we also looked at the tensile test of single straw strands for node and internode. We tested untreated straw, and you can see that the tensile strength for internode is around 66 MPa with a coefficient of variance of 10%. The H plus S, which is 30 minutes of hot water washing plus 30 minutes of a steam pretreatment, actually improves the mechanical strength, improves the tensile strength. So from 66 MPa to 88.9 MPa for the case of internode. So these are the internodes. And for the case of node, you can see obviously is a lot less compared to internode. And again, another additional reason why the node is a defect in the context of biocomposite. We cannot have such huge differences in a raw material for biocomposite production. All of the materials that go into the biocomposite, they need to have high tensile strength, which is one of the most important elements, one of the most important properties for a raw material that goes into biocomposite application. So again, another additional reason why the nodes have to be separated and have to be removed before we produce the biocomposites. You can see all the different results for different pretreatments. And when you compare them to internode, that you can see that they are significantly lower. And they are not, the nodes is not supposed to provide that tensile strength. You can see here that after failure, we looked at the morphology of the node, and we can see there are no fibers that go along the transverse direction in the stem to provide that tensile property. Here you can see a lot of, this is an optical microscopy that shows a lot of microfibers that are situated longitudinally within the node. And this is the reason why we have such a high tensile strength in the internode. We observe a very high tensile strength because we have these microfibers that are present. But the node morphology does not have any fibers, so they are not supposed to be strong in tension. They are supposed to be strong in compression. So for the context of biocomposite, we need to remove these elements because they have very low tensile strength. Another point to notice here is that the combination of mild physical pretreatments, hot water and steam, has been able to improve quite significantly the tensile strength. The hot water on its own, so half an hour of hot water pretreatment, it does increase the tensile strength. We look at it from 66 to 76, but it's not as effective as when that treatment is combined with steam treatment. The steam treatment on its own cannot really achieve a good improvement in terms of tensile strength from 66 to 69, which is not significant at all. Another interesting finding was that the bleaching or the sodium hydroxide use as a treatment, which you find quite a lot actually in the literature, it diminishes and it destroys the tensile integrity and capacity of the bead straw. You can see from 66 of untreated to 57.9. So we also proved that the chemical agents, the chemical pretreatments that are quite usual within this research area, especially for the pulp and paper industry, they are not effective at all when it comes to biocomposite production. So you can see here that the steam treatment swellens the cell wall and creates microsites for penetration of resin. And here you can see the comparison between a pre-treated sample cross-section and an untreated sample. You can see a lot wider and deeper parenchyma and vascular bundles, which basically means once the resin is added to the system, the resin can easily penetrate deeper inside the structure integrity and the structures of bead straw. Therefore, upon solidification, once you produce the biocomposite, once it is solidified, you have a lot higher mechanical entanglement between each particle, between each feed straw. Whereas in the case of untreated, you can see that the situation is quite different. They are still very tightly packed together. The parenchyma or the vascular bundles, they do not really show that depth within themselves. So the pre-treatment is quite effective in opening up the pores and expanding them so that they are ready to receive the resin and to absorb the resin. So therefore they become, we can produce high strength biocomposites. Now, moving on to the interfacial bonding mechanism, the surface, so far we just looked at the cross section, so the microstructure, but what about the surface of feed straw? The surface of feed straw is also quite important. We need to get rid of all the impurities and the waxes because wax is an hydrophobic element. We need the straw to be hydrophilic so that it can receive the resin and it can be ready for the resin system to penetrate inside it. So through our pre-treatment, which was hot water followed by steam, we were able to firstly diminish the layers of wax, clean it from all the impurities, all the fats, natural fats, and also open up some pores in order for the resin system to penetrate inside. This type of straw raw material is perfect for higher and better interfacial performance and interfacial bonding quality compared to untreated one. So this is an untreated straw which has a high amount of impurities on the outer surface and waxes. But after the pre-treatment, we have been able to remove and diminish the wax and also open up some sites, some micro sites on the surface so that the resin can easily penetrate inside. We also did some testing on a small scale of to look at the failure mechanism. You can see here in figure A, the failure that we call adhesive failure. So there are two feed straw systems that have been glued together using lignin-based adhesive, is a thermoset resin. So this type of bonding usually has very low mechanical strength because the failure has happened between the resin and the substrate. Then we have B, which we call the cohesive failure. So the failure has happened within the resin system. But there is a good bonding between the resin itself and the substrate and the wheat straw. You can see here some of the wheat straw component is still intact with the resin. Then we have C, which is a mixed failure. So you have adhesive failure at the beginning here. You can see the adhesive failure. Then you have the cohesive failure. The failure has happened within the matrix system, within the resin system. Then the substrate failure is corresponding to the highest mechanical strength. Why? Because the interface between the resin and the straw is so strong that the failure has happened within the wheat straw itself. So there is a lot higher stress required to break this sample. So therefore we have higher mechanical strength. So when does this type of failure happen? In the case of pre-treated straw. When we wash the straw for half an hour with hot water and then we dry it for another half an hour using high pressure steam. That's when we have very good interfacial bonding. And you can see here microstructure analysis. So the SEM images between that shows the interface between the wheat straw and the resin. No delamination at all in the surface and very good intimate bonding. This figure here, on the other hand, is showing the untreated wheat straw and the resin system. So you can see the failure, the crack has started in the surface and the interfacial bond, delamination, and therefore this is a representative of a weaker mechanical performing system or biocomposite. Again, here are some more images that shows the failure of a high strength biocomposite. So the straw that has been pre-treated, we have evidence after the failure. We looked at the microstructure, and we have evidence of resin penetrating inside the microstructure, inside the parenchyma and the expanded cells. And you can look at the optical microscopy images. They are useful because obviously they are in color, and you can see that the darker brownish resin, turbo-sweat resin, has been fully penetrated inside the cells of wheat straw. So the yellow component here is obviously wheat straw, and the darker component is the resin system. And in a closer up look, you can see that the resin has been able to fully penetrate inside the straw. So here I have another study to present to you based on our project. We looked at the bio-based polylactic acid composites. We wanted to come away of improving the mechanical strength. So if you're interested, you can read the whole paper, but I just show you the main results here. We used hot press in order to make our sample. So we combined PLA pellets, which is polylactic acid, with shredded wheat straw. And we hot press it at high temperatures for around 10 minutes. And we use a temperature of 185 to 190. We cut the strips of sample for tensile assessment, tensile performance assessments. And you can see the results here. They speak for themselves. So if we do not have any treatment, without any intervention, we use the wheat straw as received from the farm, and we make the composite out of it. You can see that the tensile strength is only around 4 megapascals. But if we do have that intervention, if we have a very mild physical treatment on the straw before making the composite, this mechanical strength increases quite significantly from around 4 MPa to around 10 MPa. This is showing the results for only half an hour of hot water followed by steam. This is for 1 hour of hot water by steam. And this is hot water and microwave. Actually, we wanted to see the effect of microwave in expansion of the cell walls, which is not as effective as the steam. Actually, you can see that the steam is a lot more effective than microwave. And here you can see the toughness and elongation break. And if you're interested, you can look at the details of our paper. So in order to conclude, sustainable materials, they do need a detailed investigation before we can use them and before we can get the best performance out of them. It is a very fairy tale story to just say, we have a bio-based material, we have a natural resource, let's just put it in a biocomposite or a building block and implement it throughout the construction industry. That doesn't work. We really need to study the details, specific material science behavior in order to be able to identify the drawbacks, identify the defects. Once we understand their behavior, once we understand their defects, we can build on it. We can improve them and use them for a building product. So pre-treatments are essential. In terms of future work, we are now using wheat straw as a reinforcing agent in alkali activated materials. So we don't have any ordinary Portland cement. They are made with other supplementary cementitious materials such as fly ash, GGBS, silica fume, and we want to use these wheat straw in order to see if they have the good reinforcing effect. So as I said, we are focusing on alkali activated materials or geopolymers. And the main area of our focus is on eco-friendly hybrid pre-treatment in order to improve the surface. We are going to use some nanomaterials to functionalize the surface in order for these wheat straw to have a better reinforcing capacity when they are served in the context of low carbon binders. We're not using any Portland cement, so low carbon binders with low carbon reinforcing agents, it can tell a very good story, and hopefully you can read the results of that paper once it is fully published. So thank you very much for your attention, and I'll be happy to answer any questions.
Okay, thank you very much. And that's the end of our expert presentations. We're aware that there might be a glitch due to internet issue. We apologize for the inconvenience, and the recording will be uploaded on our website, so you can catch up the missed content later. We can see now that all three experts are live on Zoom with us. Let's now give time to our Q&A coordinator, Xiao Yan, because she's been monitoring and organizing questions on both platforms throughout the webinar, and she will now feedback these questions to our experts. We'll give translation after experts' answer is finished to guarantee the quality of translation. Xiao Yan is on you now.
好的，谢谢。那么现在我们想先请问一下，第一个问题想先请问一下3个专家，就是秸秆板和普通板材相比，可以节省多少碳排放呢？秸秆板是负碳的吗？首先想请陈博士回答一下这个问题。
听到，好，那么我回答一下这个问题。就是我们要是做这个碳减排的话，就是最重要的一个减碳方式就是碳汇。那么植物呢，尤其是这个农作物，每年都会固定大量的碳。那么这个大量的碳，如果我们要是重新焚烧呢，它就又进入这个大气当中的二氧化碳了。所以这个过程呢，我们最好是通过这个大量的应用在这个建筑材料当中，形成这个比较长期的一个碳固定的方式。这样的话呢，是能够解决一部分这个碳材料的。
好的，谢谢陈博士。那么接下来请王教授回答一下这个问题，就是有秸秆板和普通板材相比，可以节省多少碳排放？秸秆板是负碳的吗？
Okay, so maybe I can chip in here. The answer to answer this question, you really need to have a very comprehensive LCA of what exact binder you are using and what exact process you are using in terms of the temperature, in terms of the pressure for compressing that board. But we know that compared to other products on the market, compared to MDF, for example, medium density fiberboard, they can save a lot of carbon. Is very obvious because the materials that we are speaking about here, they are agricultural waste. They have no other use. They alternatively will be burnt on field. So there is no doubt that we are saving some carbon, but in terms of giving the exact number, it needs a very comprehensive life cycle assessment. We need to decide on the process. We need to know the exact glue that we are using, for example, if what temperature we are using for the hot press. Is it 180 degrees? Is it 200 degrees? So these type of investigations, all these type of data need to be inputted into LCA. Once they are inputted into life cycle assessment, we can know the exact, let's say, percentage compared to the other products on market, other similar products, especially the products that are coming from wood fibers.
好，谢谢赛义德博士。那接下来请王教授回答一下这个问题。
视频要开启吧？开始吧。大家好，这个我们刚才在那个汇报当中，我们也讲到，一吨秸秆的形成可以吸纳大气二氧化碳1.5吨，所以从这意义上讲，利用秸秆做板材，它的这个降碳、吸碳的效应是显著的。但是刚才李佳你提出来的问题是 跟普通板材过去用木材来做的一个板材相比，是不是有更好的吸碳效果？普通的这个生物质材料，那个木材材料，它也是光合作用，也是碳化的。我们讲的这里碳化效应的时候，我们是因为现在木材的价值很高，我们中国呢，这个木材的资源很少，而秸秆呢大量的被浪费，没有很好利用起来，所以把这个变废为宝。从这个意义上讲，它的积碳效应是巨大的，保护了木材，减少了木材的使用，所以它的减碳效应是显著的。我们从这个角度来看啊。
好的，谢谢王教授。那么接下来我们想问一下萨伊德博士，在报告小麦秸秆的节和节间的分离是如何进行的？如果要产量化的分离，需要什么样的技术？人工智能吗？
Thank you. That's a very good question. So in my project, we propose to use laser cut and image processing. So we have a conveyor belt that these straw materials are going under this conveyor belt, and we have a high-speed camera. This camera is taking images of all these straw and is locating the node. Once it's locating the node, it gives the coordinate of the node on the conveyor belt to this laser cutter. And this laser cutter just cuts the before and after the node, and then they go on a vibrating table, like a sieve. And all these nodes, they come out. Imagine a kidney stone. When you have a kidney stone, they use laser to make it smaller so that it can come out. This is exactly the same process. It uses image processing using MATLAB or other coding system and high-speed camera. So in a way, it is artificial intelligence, but we need a couple of arrangements, all these equipments to work in a system that we can get rid of these defects in these nodes in an industrially efficient way.
好的，谢谢萨义德博士。那么接下来我们想请问一下两位中国嘉宾这个问题，就是对于小麦秸秆的节和节的分离处理，在中国有类似的处理吗？在中国市场推广的可能性大吗？这个问题请王教授先回答一下。
你好，听到吗？
应该可以听到的。
我讲讲刚才李佳提的问题。小麦秸秆节与节的分离好像据我了解，我还没听说过，我也没看到过。这个我的个人理解，这个用小麦秸秆，好在我们秸秆的综合利用关键的问题，可能我觉得还不在这个节的分离上我们是关键的问题是如何的把秸秆大量的广泛的压制成我们需要的各种性能的建筑材料。这个使用什么样的建筑材料什么样的胶lin材料和秸秆结合最好，而且又具有显著的技术经济性，就成本要低点，可能要好。第二，这个具有实用的推广价值所以我们这么多年来做的研究工作，主要是针对秸秆，大量的使用秸秆，来做大量的 秸秆材料、秸秆建筑材料，具有显著的经济效益，有显著的市场应用的可能性。还有呢，这种材料做出来就很好的有环境的适应性、耐久性，最重要的是它的耐久性。这个至于秸秆，所经过很多处理，秸秆本身是一个普通的材料。我们做广泛的做建筑材料，我们不能把秸秆，这个它的这个处理的太细否则秸秆的成本价格会很高，我们就失去了它的应用的可能性。所以秸秆利用它主要是作为建筑材料利用，它的技术经济性极其重要。否则就不会被市场所认可。谢谢。
好的，谢谢王教授。那么接下来有请陈博士回答一下这一个问题。
好，对这个问题呢，我也有我的理解。首先，在国内我们没有听说过这种技术。其实呢，这种技术是这样的，就是像刚才那个王教授提到的一样，在大量应用的这个墙体板材、墙板类的这个建筑材料，或者是墙砖之类的建筑材料方面呢，是不存在这个问题的。那么在人造板当中呢，就是高价值的人造板当中，这个阶对板材的性能影响是很大的。尤其是对这个板面的平整度啊，包括这个饰面粘贴饰面的时候会存在各种各样的问题。我们在国内这个制造企业当中也了解到了这种情况。那么如果有这种技术能够很方便的把这个阶分离出来，那么确实是能解决这个高端制造的人造板材方面的一个关键问题。所以说这种技术国内是有市场的，有需要的它对这个高端板材，也就是说国内提倡的高值化利用秸秆是有很好的这个市场前景的。
好的，谢谢陈博士。那么下一个问题还是要请问一下陈博士，就是中国在秸秆建材科技研究方面有什么举措？比如秸秆建材方面是否有国家级科研课题支持这方面的研究呢？
中国在国内有这个“12+5”、“13+5”都有支持。我们在“13+5”国家重点研发计划方面呢，做了一个课题，就是秸秆及绿色建筑材料应用与示范这么一个课题，得到了这个政府资金的支持。另外呢，我们在各个省市呢也有相应的优惠政策来支持产业的发展。所以我们一些这个技术呢已经开始得到这个利用和转化。这方面王校长、王教授他们做的就比较成功。也不光他们，我们有各种技术路线都在进行探索，尤其是对大量应用秸秆的这种技术。今后我觉得支持力度会更大，尤其是那个政府政策、税收方面的支持。
好的，谢谢陈博士。那么接下来下一个问题想问一下王教授，对于小麦秸秆、玉米秆、稻秆等不同的秸秆，在板材制备方面有什么区别？比如用的胶凝材料、预处理是否都会不同？
这个
听不到。哎，王教授，可以
哎，听到吗？
听到了，请
能听到了
您继续吧。
好，这个小麦秸秆、稻草秸秆和梅花秸秆、玉米秸秆，这个秸秆的这个材料的这个组成结构是不一样的，性能也是不一样的啊。但是经过适当处理以后，作为基础材料使用，都是很好的材料，都能够引用。而且呢，这个梅花秸秆、玉米秸秆啊，经过适当的处理以后，它的性能更优，纹理性能、机械性能会更好。但是在胶林材料上面，这个要根据不同的胶林材料啊，你采用了什么胶林材料啊？当你组成上、性能要求上，它是有区别的，一定是有区别的啊。这个从道理方面讲，你采用的是树脂材料、高质材料、胶林材料啊，还是用无机材料，这个优势不一样的啊。在总体上讲的话，这个我们目前啊所采用的这个一些材料，所使用的材料，这个胶林材料啊，实用性是很广泛的。那我们开发的这种无机的生态的复合胶林材料，可以广泛适用于梅花秸秆、玉米秸秆、小麦秸秆。谢谢。
好的，谢谢王教授。那么我们接下来是今天的最后一个问题，想请问一下3位专家，对于推广秸秆建材有什么建议措施给政府和用户呢？想首先请赛义德博士回答一下这个问题。
Okay, so thank you. This question is a really important one. They need the policymakers to understand the benefits and the carbon savings that the wheat raw material can have and enforce some laws on their use. We really need the government, the policymakers to enforce something onto construction industry main players so that they go and invest more time and more science, more research on such materials so that we can improve their technical performance. We can resolve all the issues that we have around their distribution, their transport. How can we have more factories closer to the farmers? Some processing factories closer to the farmer. And this is something, a recommendation that should come from the policymaker, from the government. We need to have more distribution of these recycling plants, these factories, next to the farms in critical locations so that we reduce the transportation. And also we need some laws that enforce the use of bio-based materials. The other issue is around the certification. How can we certify these products, these bio-based products? We need all the policymakers, all the industrial engagement so that we have all the rules in order to certify such a product. Once we certify them, we can introduce them to the market. At the moment, for example, there are no standard ways of testing such materials. I know that in China, there are some good works in terms of standardization, and we saw in the expert presentation, but we need more of that. We need a lot more of that. We need the likes of ASTM, the likes of BSI, the British and the American institutions to write standards for testing and evaluating these products, bio-based products. Once we have certified them, we can introduce them to the market. But remember, I also said that we need the investment on the research and facilities, the factories, closer to these critical locations, all these farms, so that we can industrialize the solutions. At the moment, the problem with bio-based materials is not only their technical performance, but is also their industrial upscale. how can we upscale them in an industrial feasible way, economical way?
好的，谢谢赛义德博士。那么接下来有请王教授回答一下这个问题。
应该可以听到。这个问题提得非常好啊！这个是秸秆能否广泛被利用，作为建造材料的广泛利用的一个关键啊！问题提得非常好。这个大家都知道，中国的秸秆很广泛啊。过去我们长期以来，秸秆不能够被燃烧、被焚烧，已经被法律禁止了多年的。现在呢，我们地方政府、各地政府又在推行。我在那个报告里面讲了，秸秆不允许被还田使用，作为肥料在还田使用。所以秸秆本身从政府这个行为来讲呢，秸秆已经不能够被焚烧，也不能被还田，就是秸秆应该做什么用，这个问题是一个亟待解决的问题。所以秸秆利用现在事实上秸秆要大规模利用，现在是没有了很好的路径，还找不到一个很好的路径。所以我个人认为，秸秆作为建造材料使用，这个是个有广阔的前景，很重要的一个路径重要路径。但反过来，刚才提到这个政府有什么作为这个坦率的讲，经过这几年实践，我们证明没有政府的支持和帮助，秸秆建材化、秸秆大规模重复利用是不可能的从几个方面秸秆的收集需要政府来推动秸秆产品建材产品的推广应用也需要政府来支持。政府不支持，单纯靠我们这些搞研究的同志来讲，是很难推广。这个把秸秆那个新材料作为建筑材料广泛推广应用，需要政府的支持帮助。还有一个重要的一条，大规模利用秸秆，把它做成大规模的秸秆建筑材料推广应用，这个过程当中都是我讲的一个前面大规模，后面大规模，它需要的资金，需要的开发资金是巨大的。那不是靠一个工厂、两个工厂可以解决的问题需要全社会的支持帮助，这个需要政府的帮助支持否则这个推速度会很慢。现在我们看到一个现象，大家都知道，秸秆是一个资源，没有被利用，很出秸。第二也都知道，秸秆作为建筑材料应用具有广阔的前景，大家都知道。但是，就是在推动这一个方向上，你不把大规模材料应用到实际上去，政府、社会各方面目前的支持力都相对来说还是比较小的就先有鸡蛋还是先有鸡这是一个关键问题我们觉得政府在这个方面的作用是巨大的。我们期待政府、期待社会各界都关心秸秆的利用，关心秸秆建筑材料的推广应用。我认为这个7年具有广阔的应用前景。现在我们开发这个材料性能很好，价格成本很低，亟待开发利用。我们现在的困难需要政府的支持，我们的困难我们缺少广大的这个资金。谢谢。
好的，谢谢王教授。那么最后有请陈博士回答一下这个问题。
好，这个问题 我谈2个方面，就是我所了解到的。第一个就是实际上这个除了成本一个问题之外，我们整个链条还是需要打通的。比如说我们设计部门能不能采用我们的建筑部门能不能采用我们的这些新的建筑材料。那么这方面呢，我们是需要得到支持的。这是一个其实我们现在解决的呢，主要还是一个市场的问题。市场问题比生产制造问题还要复杂的多。一是需要政府的支持，另外需要各个企业的支持，另外需要建筑部门的支持。需要我们标准图集等各个方面的支持。另外一个呢，就是说政府来怎么支持，其实是制造部门也存在一些问题。比如说初期投资是非常大的，就像刚才王教授提到的，初期投资比较大，那么也有很大的风险。这种情况下，这个探索是需要得到政府部门的支持的。一个是资金支持，一个是吸引这个社会上各种基金来支持。这是一个问题。还有一个问题就是收储问题。其实收储问题呢，现在是又不让烧，又不让还田，那么只能用在这个燃料上，用在这个饲料上，其实用在鸡料上，最应该得到支持。就是说我们政府部门在这个物料化上不能只偏向1、2个，那么应该有综合性的政策来支持在我们建筑行业发展。固碳的作用是最简单最有经济的高质化利用的一个方式，那么这就需要相应的配套政策的支持。这样的话呢，我们是社会各个方面的力量的共同应用，来解决这个固碳减碳的这么一个大目标。我觉得在建筑部门来大量应用秸秆，尤其是每年都生长的秸秆，是固碳的一个非常好的方式。那么也是我们值得投入精力、投入资金、投入力量，来发展的一个有前景的行业。我的观点就讲完了啊，谢谢大家。
好，以上就是今天全部的问题了，谢谢各位专家。
Okay, so that marks the end of our Q&A session. Thank you so much, everyone, for staying with us. Please scan the QR code on the top to join our WeChat group, or on the bottom for our LinkedIn group to continue the discussion. The next series are planned to be held next year in 2022. We welcome any feedback on topics that you would like to hear about, and any feedback on possible improvement of the series. And last but not least, the recorded video of today's session will be uploaded on Arcus and Callisto's website and YouTube. Thank you very much, and I look forward to seeing you next time. Bye, everyone.
好的，谢谢。那么现在我们想先请问一下，第一个问题想先请问一下3个专家，就是秸秆板和普通板材相比，可以节省多少碳排放呢？秸秆板是负碳的吗？首先想请陈博士回答一下这个问题。